All right, looks like we are live. Welcome to Standing for Truth. My name is Donnie B, and I am your host for tonight's program. This is day one, session two of the Standing for Truth Ministries Defending Genesis Conference 2022. We just a couple hours ago finished session one with Sal Jardina. He's a professional geologist, very knowledgeable, and he gave a presentation titled The Relevance of Genesis. And we did over an hour of discussion and audience questions and answers, mostly pertaining to the Genesis flood and evidence for the worldwide flood. Now, session two features TRock. And TRock, he's done a ton of research into the creation versus evolution topic. He has also had numerous debates with some serious students and apologists of evolution. This includes some well-known evolutionists like Conspiracy Cats, who he's debated specifically on this topic of isochron dating. That's what we're doing during this conference, guys. We are taking on their best arguments, and we are taking up their challenges, the evolutionist challenges. He's also debated Mark Reed, T-Jump, Luca Medugno, Mark Drysdale, and so many more. So TRock, he is a warrior who's not afraid of a good challenge, and I appreciate him. I appreciate all the work and study that he's put into these important topics. As a matter of fact, he is one of the faces of our Evolution Debate Challenge series that we have been hosting. This challenge we have been advancing in 2022. He has joined myself, Matt from the Standing for Truth Ministries channel, Kent Hovind, and Professor David McQueen in being a part of the debate challenge this year. Tonight's show is titled The Isochron Method and Other Dating Duds. TRock, thank you so much for being willing to contribute to our 2022 Defending Genesis Conference.
Thank you, Donnie. Thank you for having me. It's an honor to be here, and thank you to the audience for tuning in. Kind of look forward to hearing some input from the audience and hearing some Q&A.
Absolutely. Absolutely, brother. I am pumped for this. This is an important topic that I think needs to be dealt with thoroughly and sufficiently. There's not a whole lot out there on isochron dating, and as anybody who follows this ministry knows and understands, we like to tackle their best arguments. In the realm of genetics, we like to deal with endogenous retroviruses. Here in the realm of dating methods, we like to deal with isochron dating, the heat problem, topics such as this. So before we get into it, a couple shout outs to some supporters. George Bond says TRock rock. So I completely agree. Thank you so much, George, for your support. Steadfast and Easy, $5 super chat, says, hi, everybody. God bless all. Let's date. Yeah, that's dating method. So thank you, everybody in the audience, for being here. God bless you. I want to let you know the format for this show is going to be about a 40-minute presentation from TRock. Again, the topic, the isochron method and other dating duds. And then we're going to do some interaction with you guys in the audience. We're going to take some audience questions. So you have 40 minutes roughly in terms of the presentation to shoot me your dating method related questions. And we are going to have TRock engage them. So with that being said, introduction out of the way, TRock, my good man, I'm going to hand it over to you. And the floor is all yours.
Thank you, Donnie. I am sharing my screen now.
Okay. Looks good.
All right, let me put this in read mode. All right, so we are defending Genesis. Genesis, of course, is an accurate eyewitness written history of the world, and what we expect to find in scientific studies of the age of the earth that exclude the biblical history is that dating methods are just difficult to navigate in a strictly scientific context. And I think that's exactly what we're going to see. I'm going to start by reviewing some preliminary methods, not Isochron, and somewhat chronologically in terms of how much time can be quote unquote measured by each method, and then I'll build up to isochron dating. So the question is reliability of isochron dating. Can we count on it? And I am saying no. It's actually fraught with problems, just like pretty much all of the other dating methods. So an overview of dating methods. Carbon-14, very popular method. It's used for more short-term kind of dates, roughly from 500 to 50,000 years old. You might hear people say up to 100,000 years. That's a theoretical limit based on sensitivity of a mass spectrometer and whether it can count that few of atoms in a sample. But 50,000 is typically the accepted limit based on roughly 10 half-lives. It's most reliable from the 500 years mentioned earlier to about 3,000 years. Beyond that, it frequently has to get cross-checked by other methods such as VARVs, oxygen isotope ratios, etc. I might also mention that even within the short term, 500 to 3,000 years, it frequently gets cross-checked against known archaeology. And that's kind of an important idea, because essentially what you're doing is you're verifying a dating method, a chemical dating method, with an eyewitness account. And so it's also worth noting that the eyewitness accounts are used to basically fix positions on a carbon-14 plot in order to calibrate it, at least within the range of written history as secular science accepts it. So C14 is used on biological materials such as wood, bone, soft tissue, paper, that sort of thing. It is not used on things thought to be excessively old, such as coal, dino soft tissue, oil, or amber. And there's a reason for that. It's because no matter what age you get from them, they're going to be rejected, because hypothetically, or in the theoretical world for carbon-14, in 1 million years, if the planet were made entirely of carbon-14, planet Earth was entirely carbon-14, 1 million years would be enough time to have it decay away down to the very last atom. So nothing, the most sensitive equipment imaginable, should not be able to detect a single carbon-14 atom in anything 1 million years old or older. So, of course, I'm not going to go into great detail here because this is just an overview, but coal does have carbon-14 in it. Dino soft tissue does have carbon-14 in it. Oil has it. Amber has it. And I didn't list it here, but diamonds have it. Of those examples, I suppose diamond is the most difficult to explain because it's the easiest to clean. It's the least permeable material, that sort of thing. So contamination doesn't really fit well with diamonds whenever they're dated. Okay, dendrochronology. This is the counting of tree rings to determine age. It can also be used in conjunction with carbon dating and accumulated across successive deposits by overlap. And that overlap can happen in a couple different ways. One of them is you've got two different trees, for example, with enough rings present, and the strata literally overlap each other. One will be deeper than the other, so you count down to one and then kind of jump into the other one. The other way that the overlap is done is you count the rings of the first one, then you use some biomaterial in the proximity of that, or that first tree, and often it's a living tree that's started with, but it doesn't have to be. But anyway, use some biomaterial and carbon date it, and then oddly enough, use a linear extrapolation to jump to another sample that's supposedly older than the first tree rings that were counted, and so they can be added together that way. So typically, a living tree is needed as a starting point, but not always. Fragments of wood or plant debris are carbon dated to connect one tree to another. Has been used to date up to around 11,000 years, what they call fully anchored. In other words, you have a real good reference frame for each of the dating extensions that you're putting together to make this 11,000 years. Okay, many rings can form in a single year, though. And extra rings are indistinguishable from annual rings under a microscope. So, two of the issues with dendrochronology is exactly this, that you're basically extrapolating carbon-14 dating that's outside of written human history. So there's no archaeological context to put in there, which is kind of a bad thing, because you have no way of accurately calibrating your carbon-14 at those extended ages beyond, modern history in the archaeological context is typically perceived to go around 5, 6, 8,000 years as far as writing goes, actually probably closer to 5,000 years. And then beyond that, of course, for just tools and stuff like that. But even those are, because the older stuff has no writings with it, it's also highly subjective to try and use those as some kind of anchor point, so to speak, for calibrating carbon-14. Donnie, I'm going to stop real quick. Is my audio still good?
Yes, it's coming in real good, TRock.
Okay, thank you. Okay, and then we have varves. Varves are thin layers of sedimentary clay deposits. These are formed by seasonal fluctuations in glaciated areas. That's at least one way they're formed anyway. They often alternate between light and dark layers that correspond to winter and summer seasons. Varves can also form in lake bed sedimentary deposits. They're used to estimate ages to around 20,000 years as far as ages go. However, we'll find out in a minute, there's a little more to it than that. Can alternate between coarse grain and fine grain. Light color layers represent winter, dark color layers represent summer. And they've been used to estimate millions of years. So varves in lake beds, this is two slightly different things. The previous set was for varves in glacial environments, but varves can also be found in lake beds, and they've been used to estimate millions of years. Now we're talking more relative kind of dating typically here, but when a geologist or a paleontologist is looking at varves in what they consider deep time, they might be counting lake bed varves and estimate they're almost never counted, one by one. They're estimated by their thickness and of each individual layer compared to the thickness of a formation that they're found in. And so it's somewhat of an extrapolation, which is not unreasonable, but you can have millions of varves in a single formation. And so to them, that represents millions of years of deposition in a lake bed. But the problem is they can be formed by hurricanes or rapid underflow. Each individual varve can be formed that way. And they can be formed, many of them in a single year. So they pose another problem for dating methods. And not unlike any dating method, it's the assumptions that every single layer has to be, either seasonal, half a year, or one full year. Those assumptions are generally just not warranted, because we do know of so many examples where where those specific assumptions are shown not to be true in modern history. The other assumption that this process has happened more or less uniformly over millions of years is also not warranted, because most of these lake bed deposits do not have the bioperturbation, for example, insects and animals, worms, that kind of thing, burrowing through the layers. They're typically not enough. Sometimes you can find them, but there's typically nowhere near enough to account for that much time. And so erosion is also typically absent. So you can get these very wide spread areas with varves in them, but the erosion that should be present over that span of time is just not there. The layers are too even, too homogeneous, and do not indicate the passage of time at all. Okay, so we're going to move on to radiometric dating, single isotope decay. So this measures the amount of apparent radioactive isotope and its stable daughter isotope, such as lead, uranium, lead, and so on. These amounts can be converted to an age by the standard equation NT equals NO times E, to the negative KT, where N sub T is basically the amount of parent, or the amount of the radioactive element that you have now, and N sub O is the original amount that you started with. Ominously, though, this equation is missing an extension. You can build this equation out if you wanted to, because this standard equation always assumes that there's no daughter isotope present in the original sample. So there's no term included on here for it, which is an unwarranted assumption, because there's no way to know that other than perhaps taking radiometric samples of rocks of known age as a reference point to evaluate them from. It would be called a control group in a proper scientific study. You would go around and gather rocks from across the globe, or whatever area you choose to study, and basically measure the isotopic ratios across a broad number of samples, and that would be your control group before you go trying to apply the method to formations or rocks of unknown age, so to speak, such as submarine volcanic formations that nobody's in history could have possibly witnessed. As far as I know, that practice is not actually done, because it won't yield the results that deep time advocates expect to see. So uranium lead is used for dates greater than 100 million years. Argon, for example, is used for dates less than 100 million years. That now I'm only giving two examples here. There are many, many examples that could be used, but the problem here is they all follow this this kind of ideology where you have to already know roughly the age of the sample before you can even pick a method for it. So that's kind of a major red flag. If you already have to know the age of it, something's kind of wrong. You're kind of picking what you want your results to be at that point. Okay, so issues with single isotope systems are that all rocks are open systems. There's no such thing as a closed system in a rock formation in the Earth. Many radioactive isotopes are water soluble. Uranium, for example, and lead are both water soluble. So in an open system, this creates huge problems because water or water in some form, steam is a real common ejection from volcanoes, for example. And so with all this steam and water percolating through the mantle, you start out with a problem with most radioactive isotopes, because you're already rearranging the chemistry during the formation process. So also many radioactive isotopes readily form ores with other minerals. Uranium is notorious, of course, for forming several ores and has to be refined. So it's very difficult to say that these open systems have not been drastically affected especially over deep geological time. Okay, now that brings us to isochrons. So introduction to isochrons. Isochron dating. This measures the amount of a radioactive parent isotope, its daughter decay product, and a stable isotopic variant of the decayed daughter. The daughter and its isotopic variant are isotopes of the same element. So the most common example, and the one I'm gonna kind of start with, one of the most common examples is the rubidium strontium system. So the word isochron literally means same age, iso, same, chron, age. It's an alternate form of radiometric dating specifically for deep time. It requires a radioisotope whose daughter product has a stable non-radiogenic isotope variant. So the common candidates are rubidium-87, strontium-87, strontium-86, samarium-147, neodymium-144, neodymium-143, lead-206, lead-204, lead-207. Those three systems are just examples that are commonly used. It does not require knowing the initial amounts of parent and daughter isotopes, which is supposed to be a big plus for the method. We'll find out later that it's actually not. it plots the ratio of radioactive parent to daughter product on the x-axis, and then it plots the ratio of daughter product to daughter isotope on the y-axis. So basically, you're just trying to find a line out of two ratios that are going to equate to some constant that you can plot on a typical XY Cartesian graph. Okay, and so this is kind of what they look like whenever they're plotted. This is from the Brahma amphibolites. And so sample chart A there shows rubidium strontium system, and you can kind of see how these points plot out here to form what looks like a line. You might take note here, it says isochron plots for the Brahma amphibolites. The crosses and ellipses are the data points, sample analyses, and their sizes are proportional to the plus or minus analytical errors. Okay. The analytical errors have to do with counting, and that's it. Literally just how accurate do you think you counted the isotopes. So you also have chart B is samarium neodymium, chart C is lead, just three different systems. Now, this particular example is showing one of the many problems with isochron dating. It was actually supposed to be a solution to single isotope methods. So I'm backing up a bit, but the known problems with single isotope methods were what I stated, is that it was too easy to account for isotopes drifting in and out of a system because they're not closed. And so essentially over the history of radiometric dating, what many scientists discovered was that they couldn't always trust the dates they were given from the samples. So they sought another method in isochron plots. But as it turns out, the isochron method has pretty much all the same problems that the other single isotope methods have. But it's going to have another unique problem that is quite different and doesn't help at all. But either way, basically, when you look at isochron plots, you come to the same types of problems. You get dates that just don't make sense. And so this is one example here. This is showing an isochron age for the Brahma amphibolites for rubidium strontium that shows 1.24 billion years. The samarium neodymium of the same sample gives 1.655 billion years, and then the lead isochron system for the same sample gives 1.88 billion years. So you might note that the plus or minus values on each one of those is well inside the distance between the ages that are given by each method. So this is not a case where the error bars overlap in some way to try and give some kind of concordance between the methods. Three different isochron plots just register incorrect dates. So if you're a geochronologist or a geologist, which date do you think is right? It becomes super subjective at that point. Something else I want to point out here too about these graphs. Now, you have to get an actual plot to really kind of figure this out, as in an actual spreadsheet plot, so that you can kind of zoom in on these numbers, because it's not totally obvious right here. But if you look at the x-axis across these, it goes from 0 to 2.0 on this rubidium strontium, and it goes from 0.69 to 0.74 on the y-axis. So what you're seeing, though, is those plots are actually very, very close together. Now, mathematically, and I will concede, mathematically, it doesn't technically matter, but it is a really small area that you're looking at trying to find a best fit line for. And I think the biggest problem for me, like I said, mathematically, that should not technically matter, but the problem is that there are so few samples that are used for a given analysis that it's hard to have any real confidence. There is a thing called a confidence interval with statistical analysis on things like this, and that confidence interval is there's basically a formula for calculating what that confidence level should be. Notwithstanding, it's still a very subjective idea on how confident you can be whenever your sample sizes are actually quite small. They're considered large, I get that, but if you know a little bit about statistics, these are typically done with something like 6 to 10 crystals, zircon crystals, to count the isotopes in, but these particular samples, I think we'll find later, I'm not sure if I have it in the slide set here, but these particular samples actually used almost double or even triple what typical samples use. So that they used a higher count, which is also a little bit odd here to get such different results across 3 different isochron systems. So what I'm suggesting is increase the number of zircon samples that are analyzed, and the plot may become quite fuzzy if you get enough of them, and you couldn't plot a line. I'm going to come back to another idea, but we're going to come back to this in just a minute. I'm going to continue on for a second so I can kind of explain what they're trying to do here. The y-intercept is greater than 0 in an isochron plot. As you can see here, each one of these starts out somewhere above the 0 line. The y-intercept represents t equals 0 for the sample. That means, going back here, I don't know if everybody can see my mouse or not, but that point right there represents t equals 0. Okay, the linear relationship between ratios of stable isotope and daughter isotope and the parent daughter isotope demonstrate an isochron. That's a linear relationship. Nonlinear relationship demonstrates migration of isotopes or other contamination and invalidates the isochron. So if you can't get a line out of it, and actually what they're doing, I don't have the information here in front of me, but what they're doing to do a best fit line, if you open up an Excel spreadsheet and kind of plot some stuff out that looks like it's in linear fashion, you can tell Excel to plot this line for you, and it will typically give you what's called an R-square value, and that kind of tells you how close the data points fall on the line itself. So like what's real common is an R-square of above 0.95 is considered good, and if it gets very far below that, it's considered bad. So an isochron just won't be valid if that R-squared number gets too low. Okay, and because it will indicate that it's a non-linear relationship. The entire isochron line, now this is not true for all systems, but most of them do follow this. The entire isochron line rotates counterclockwise as theoretical age increases. So what you're saying is the slope of the line is going to increase going uphill counterclockwise as the theoretical age gets larger. Okay, it's commonly uses 6 to 8 crystals per sample, but may use more, which is precisely what happened in these samples, is they were in the range of 17 to 20, I think, to do these dates. Okay, where and why it's used. It's used on igneous and metamorphic rocks that come from sources whose origin is not known from historical accounts, such as Grand Canyon, marine volcanoes, etc. This is a red flag. It can't be used on anything in known history because it's going to yield a false isochron. It's going to render a bad date if you're able to plot an isochron, an actual linear isochron at all. You're already going to know it's bad. So to me, that makes no sense that you would go looking for something of unknown age to try it on. But nevertheless, it does eliminate some of the assumptions associated with single radioisotope methods, such as potassium argon that assumes all argon escaped prior to solidification, or other types that assume there was no daughter isotope present when the rock formed. The uranium lead system that I mentioned earlier is one of those. You basically, in the single isotope system, like I said, you do have to worry about migration of both the lead and the uranium in and out of the system because they are water soluble, and they do form compounds with and ores with other elements. So that's why this system was developed, to get rid of those assumptions. It's alleged to provide 2 clocks running simultaneously that demonstrate no migration of parent daughter or isotope of daughter has occurred. The 2 clocks, now one of them is radiogenic, the other one is not. So you're really comparing isotopic ratios that are supposed to stay at a constant ratio over time, as opposed to 2 literal radioactive elements decaying at independent rates but converge on the exact same date, which I think is odd, because I would think that would be a much better way to approach it. But this method is chosen instead, presumably because you run into problems with trying to get 2 radioisotopes to converge on the same date in any one sample. It's probably kind of rare, I would suspect. And when it does happen, you probably get a lot of anomalous dates out of that too. Okay, so isochrons are preferred over single isotope methods because those are known to be unreliable. Isochrons are also used for more ancient dating because C14 methods are considered to not be valid over 50,000 years, as well as a host of other methods. They just are not considered to be valid that far out. So isochron is basically limitless. Actually, I'm going to back up here. The rubidium strontium, rubidium-87, has a half-life of something like 48.8 billion years. Could you imagine if you had a rubidium strontium isochron plot that gave you a date of 20 billion years? It's hypothetically possible to find such a thing, but no geologist in the world would accept that date because it's older than the universe. So what assumptions are involved in isochron dating? Okay, no parent or daughter isotopes have migrated into or out of the samples. Now, when you look at this slide here, what you're seeing in blue is they're the ideas that I'm actually not going to contest. The red is what I will be contesting. So I'm not contesting the first bullet point there. No parent or daughter isotopes have migrated into or out of the samples. The rate of decay has always been constant. I'm not really arguing against that either. You can say the rate of decay has always been constant, and I'm not even going to invoke accelerated decay as a starting point either. So I'm basically giving that as a valid assumption. Here's the problem I have. 100% of the daughter product was derived through standard radioactive decay processes. This is a problem for a couple obvious reasons. Number one, it is an open system that you're investigating, and it is supposedly millions, sometimes billions of years old. And so you have to ask yourself, how in the world did you not end up with migration into or out of this open system? Okay, and then the other assumption is that you started with homogeneous parent stable daughter isotope. It's kind of irrelevant. We'll see why here in a little bit. I'm not contesting that point. Okay, assumptions challenged. 100% of the daughter product was derived through standard radioactive decay processes. This is naive. The very processes that created primordial, pick your radioisotope, uranium, rubidium, potassium, samarium, etc., likely also created its daughter product at the same time. Even in the secular view, that's almost certainly got to be true. No event has happened in the millions or billions of years the sample supposedly existed that would have obscured the dating results. That's another basic assumption. This is also naive. No volcanoes in recorded history have a proper isochron signature. So how does a volcano inherit a true isochron profile if none of the young ones start out that way? It's just special pleading. Okay, and then another assumption is started with homogeneous parent stable daughter isotope. This is also irrelevant, even if it's true, because you still don't know what the starting point, how the sample originally came to be that way to begin with. So it's kind of irrelevant. Okay, so we've kind of talked about some of these issues, but I'm going to go over them again. Open systems, you have a problem with ore texture, mineral chemistry, supergene alteration through oxidation, parent-daughter disequilibrium through chemical or radioactive means, groundwater and soil chemistry, so pH, EH, salinity, adsorption, that sort of thing. You can find this stuff at creation.com, the failure of the uranium, thorium, lead dating at Koongarra, Australia. And then, of course, it's what I've been arguing all along, the origin of primordial parent and daughter elements. And I've got a graphic we'll look at here in just a second to kind of demonstrate what the problem is with primordial isotopes. Okay, so there's a plethora of foreboding terms associated with isochron plots from the open literature. These are mainstream science discoveries. And so what's happened is there's apparently quite common to come up with what's termed here 9 different ways: pseudo-isochron, apparent isochron, false isochron, mantle isochron, secondary isochron, mixing line or mixing isochron, an erupted isochron, an inherited isochron, or a source isochron. And you can find this under this creation.com article. And for those in the audience that might be interested in actually going to these sources, if you're a skeptic or a deep time advocate, I would absolutely go to these sources that I'm showing here, because when you go to these articles, I realize they're creationist literature, but they will point you to mainstream science articles that this stuff originates from. So it's a secondary source, I get that, but the primary sources are available through this link. And you can go investigate that. The origin of primordial parent-daughter elements, anomalies in isotope ratios in meteor rocks. There are anomalies out there, just like every other dating method. There's nothing new about finding anomalies for any given dating method. Isochron certainly is not outside of that. So, for example, strontium-84, strontium-86 compared to strontium-88 and strontium-86 in the Murchison meteorite. You can see that here at this article titled Contra Rubidium Strontium Dating. Basically, some of these are actually stable isotopes, but it alludes to a problem called fractionation with radio or with isotopes of certain elements. Actually, many elements have a somewhat there's a process called fractionation. It refers to basically the separating of isotopes of the same element in a sample, and so there are ways that happens naturally in the earth that basically disrupts the whole point is here that when you find these examples of fractionation, it disrupts the what you would think would be the original isotopic ratios from standard radiometric or decay. So fractionation is just a process that distorts how you interpret those ratios to even get an isochron plot. Okay, so this is somewhat of a joke, but it's actually this is kind of the heart of the problem with isochron dating, and that is that isochron plots can be generated from just about any mixture if it's homogeneous. Random numeric simulations, physical models of mixed substances. Homogeneous state can simply be the result of physical mixing. See the previous slide for isochron terms, and that's exactly that. This bullet point number 6 exactly makes that point. It is literally called in the open literature a mixing line or a mixing isochron because this is true. I've actually done this myself. I put this second bullet point on here because I went through an Excel exercise where I basically used some random number generation. And all you need, because isochron dating requires 3 components, the parent, the daughter, and then the stable isotope of the daughter. So in a random numeric simulation, you basically just kind of replicate that idea with, say, for example, 3 number ranges that are kind of, that don't overlap, and they're kind of distant from each other in some way that you can put them back together as ratios, just like isochron is done. So the M&Ms, for example, you need 3 different colors of M&Ms. If you would need a rather large bowl, granted, for M&Ms because the M&Ms themselves are pretty big, and to get any kind of decent linear plot out of that, you need a pretty big bowl with a lot of M&Ms in it. But 3 colors is all you need to match the 3 components of a standard isochron. Probably better is doing something like this cinnamon and sugar example here. You can see on one side, it's kind of a trick question. If you put a cup of cinnamon into 3 cups of sugar, what will the ratio be? Well, the answer is you don't know, because it totally depends on how you mixed it. If you don't mix it at all, you might not get any cinnamon, or you might not get any sugar, depending on the sample size you take. If you mix it partially, you might get what looks like an isochron in some places, but in other places inside that same bowl, you would not get a linear quote unquote isochron plot. But if you thoroughly mix the bowl so that it is obviously fully homogenized, you're going to get exactly what you put into it in your isochron plot. You're going to get 1 part cinnamon and 3 parts sugar, period. And I mean, that example only has 2 components, but add a 3rd component. And when you break the ratios out, just like isochron plots are done, you're going to get the same thing. You're going to pull, per the standard method, 6, 8, 10, 15, 20 samples, it doesn't matter, count the colors of each one, and then make your numeric ratios and plot them out, and you will get an isochron plot out of powdered sugar and cinnamon and perhaps one other ingredient that's easily identifiable. But the point is that isochrons literally are just mixes. That's all they are. There's no way to demonstrate anything else but that they are mixes. So I would encourage people to actually try this for themselves. If you know what you put into it before you mix it up, you know what you're going to get out of it. If you don't know what you put into it, you can make the plot, and then once you get done with the plot, you'll know exactly what you did put into it, because the ratios are going to come out, if it's thoroughly mixed, exactly how you put them in there. So there are a plethora of bad examples that can be investigated here. Concordant isochron at Cardenas basalt and associated diabase of Eastern Grand Canyon. We can go through each one of these. I probably won't try and drill into each one of them due to time constraints here. But the point is that just like all other dating methods, there are anomalies found all over the world. This is at Somerset Dam, in Amorphic intrusion in Australia, Kungara, Australia, Mount Ngaruho, I believe that's pronounced, in New Zealand, and so on and so forth. So isochrons don't really provide any better reliability for dating than any other method that's out there. And so on the closing notes of primordial elements, you can kind of see the problem here. Isotopes in the secular paradigm, for any elements heavier than lithium, they're supposedly created during supernova explosions. But the problem is it's a random explosion, and you don't know what ratios you're getting any isotopes in. If this even worked, it's purely hypothetical. Actually, it's not even theoretical. It's purely hypothetical. If this even worked to produce heavy elements like rubidium and strontium, how do you know what ratios you're going to start out with? You're almost certainly going to get a broad spectrum of isotopes of any given element, such as strontium. And then, of course, there's on the Earth itself, you have the problem with the fact that it's a molten liquid in the core, and the secular paradigm requires billions of years that the Earth has been here, which basically means that the mantle, being the liquid that it is and relatively low viscosity for otherwise solid material when it's cooled, it's basically been percolating and circulating in the Earth's inside the Earth for billions of years. How can it not be anything but a mixing line like this? And so the fact that you do find non-isochron plots is actually perhaps could be construed that the Earth really isn't that old, and that this mantle material has not been mixing that long. So with that, I wanted to bring out one really super important point about isochrons. And that is, what if you found the perfect isochron? Here's the kicker. The perfect isochron, to me, basically implies that the ratio of the parent and the daughter is exactly perfect in every and equal in every single sample that you take. So, for example, if you let's say it's rubidium 87, strontium 86 on the y-axis here. If every single sample, let's say you pulled one sample and it had, and I'm just throwing numbers out here, but let's say it had 3 rubidium atoms and 4 strontium atoms, and then you grab another sample, but you count more atoms, and let's say you got 6 and 8 that time, and then you count another sample, and let's say you got 12 and 16 in that one, and you just keep on doing it. But if you pay attention to the numbers that I rattled off, every one of them crunches down to the exact same ratio. What that means, and if that were true on the y-axis with the daughter and its variant, if you had the exact same thing happen there, what you would get is literally a single dot. That's it. You would not have a whole bunch of dots. You could have as many samples as you want, but if they all come out to the exact same ratio, you can't get a line out of it because all you can get is a dot. Every one of them equals the exact same thing, and the ratios fall on the exact same point on the graph. So there's no line that can be drawn from a quote unquote perfect isochron. So with that, that was kind of the highlight of the presentation, is that you can mix anything and get an isochron. If it's too perfect, all you're going to get out of it is a dot anyway. So Donnie, I am wrapped up with my part of the presentation, and we can move to Q&A if you would like.
Awesome. TRock, very good job. Very comprehensive, very technical. So I think the T in TRock stands for technical. I love it. Great work. And yes, we got some solid questions here. I guess a question of my own, TRock, for you, out of curiosity. So the fact that we see so many discordant dates with all of your dating methods, including isochron dating, which, as you know, since you've had many debates with evolutionists, they'll try and say, okay, some of the other dating methods, like, potassium to argon dating, for example, yes, we get, discordant dates, and there are some issues. But isochron dating, on the other hand, requires little to no assumptions. Would you say that the discordant dates imply that the Earth is young rather than old, because there's really no consistency? Go ahead, TRock.
Yeah, no, that's a great question. Discordant dates, what do they imply? Well, the very fact that you could identify them as a discordant date tells you that you basically have to know the answer before you get the answer. And so what does that tell you about any date? I mean, every single method that I've listed so far has an association with discordant dates. So the most obvious to me is carbon-14. You can have discordant dates with carbon-14 in the very near geological history. If that's the case with things that are used to date things of very quote unquote young age, and I'll just use a number, 1 million years. If you can have discordant dates in the 1 million year range, what makes you think you're ever going to have reliable dates in the 4.5 billion year range? It's pretty much absurd to think such a thing. And how do you know any given date is discordant? Well, basically it boils down to what I alluded to with carbon-14 calibration. Carbon-14 is calibrated against eyewitness events, i.e. archaeological finds and writings and that sort of thing. Because if you have an archaeological find that you can nail down a timeline to, and then you go and perform a carbon-14 analysis on it, and it gives you a different date, which date do you throw out? Do you throw out the archaeological date, or do you throw out the carbon-14 date? So basically the extrapolation, the fact that problem does exist, to answer your question most directly that I can, the fact that problem does exist in younger quote unquote methods absolutely implies that finding discordant dates among the deep time systems basically just tells you that the Earth really is young.
Well, I find it so funny because in my experience engaging the proponents of deep time evolution, is they want to put so much trust into the dates derived from rocks of unknown age, right? But the rocks that we actually date here of known age, where we understand when they were formed, we can't even get those right. We get the ones of unknown age, they just want to put what seems to me blind trust into those debates, or into those dates. And George Bond has a comment here, and then feel free to give your input, TRock. George says, radiometric dates corroborate each other, especially if you throw away all the ones that don't.
Yeah, that's quite humorous. Thank you, George. No, it's a great point, because essentially the calibration exercise in general that I was referring to, you're basically taking and extrapolating and trying to recalibrate on an extrapolation. Now that term may be a little fuzzy to people who don't have a science or an engineering kind of background, but extrapolation is where you basically have a data set and you try and find a value that's well outside. Well, it doesn't have to be well outside of your data set. So there is some warranted use of extrapolation, but it's typically very limited. So in engineering, you can extrapolate on things like temperature and pressure for gases in a heat engine kind of situation, but you can only do it with a very narrow range outside of your data set. After that, you've got to go find a different method or get some new data that puts you in the realm of the scenario that you want values on that you don't have. You have to be in that range. So personally, having taken engineering courses, I'm sure George has too, when you go through book exercises, they'll give you a table of values to do some of these mathematical computations on. For specifically, what I'm got in my mind is the temperature, pressure, and energy metrics from a heat engine. You can get a table of values, and you're going to basically use some formula that they're going to give you, and you're going to try and calculate a value that's not actually in the table, but it is inside the data set in some way or another. It's just that exact value isn't represented in the table. Well, sometimes they deliberately kind of put you out on the edge of that data table that they give you, so that you have to do one of two things. Either you have to know how to extrapolate to get it, or you have to have a completely different mathematical means of arriving at it with the information you have. So the point is that in the real world, they strongly discourage extrapolating like that. So when it comes to radiometric dating, that's all it is a series of extrapolations on top of extrapolations. And in practical engineering, that's a catastrophe.
Right. Good points. So here's a question that comes in from, let me see here, right here, Doki Doki Bible Club. So Doki asks, once in a while, several different dating methods give the date. So this goes along with what we're talking about. We get a lot of discordant dates. We get a lot of rocks of known age. Test it, right? We know when the eruption took place, the rock was formed. We test it, and it comes back at millions to billions of years old. But yet it was just formed recently. That's kind of crazy. But once in a while, and here's the question: we'll get a date range that evolutionists are actually looking for. So his question is this good evidence?
Okay, so taking his question, thank you for the question, Doki. With several different, can you put that back up there? Because I want to pay attention to the specific verbiage he's using here. With different dating methods, give the date range. Several different methods give the date range evolutionists are looking for. So what he's saying is, let's say for example, kind of short term, not isochron, but it's the same concept. Let's say you carbon date something and you get 12,000 years. That's obviously beyond biblical history, right? But what if you do VARV dating and you get something like, let's say 12,500 years, and let's say you do some kind of oxygen isotope dating and get something in that ballpark, 11,800 years or something like that. This is kind of what it looks like Doki is referring to, and it's an argument that is commonly used. And is it good evidence? Absolutely not. And the reason is same things we've already talked about. That is the calibration method for how you determine whether a date is valid or not. You basically have to have some starting point that you're using as the calibration reference and building off of that. And the problem here in this example, so I'm saying varves, oxygen isotopes, and carbon-14. The problem is one of them is probably the calibration basis for the other. And if it's not, it might actually, so the carbon, for example, might actually have a calibration against geology, or possibly, more specifically, something like archaeology. There are archaeological digs that are considered to be in that range. And so somebody might have went and dug up a bronze axe, for example, and said, oh, this is, 11,700 years old. And then they carbon date the handle and go, oh, what they're doing is they're going to take the archaeological age. In some cases, it can go either direction, and that's part of the problem. It can go either direction. You can calibrate one with the other, or vice versa. It's whatever the scientist thinks is warranted. And so the point here is that these different methods that supposedly converge on the same thing are actually calibrated against each other. So it's pretty much completely meaningless, i.e., what we commonly say, circular reasoning.
Great answer to a great question. I study the hominin fossil record and human evolution in great detail, and especially when it comes to that field, they will very frequently get inconsistent dates, right? So they'll derive a date that's inconsistent with their ape to man evolutionary story, and they either redate it until it comes up at something that works for their story, or they just discard it in general. So it's really sloppy science, and you'll get proponents of deep time evolution arguing for an old Earth so confidently from dating methods, when, as you're demonstrating here, even their best so-called dating method, isochron dating, we get lots of discordant dates. So I guess a question that I have for you, TRock, would you put accelerated nuclear decay during the flood period? Would you hold to that position, or?
Personally, from the rate project, and that's a great question, because in debates, and if you go back and look at some of my debates where this is brought up, the quote unquote heat problem, there's actually more than one heat problem, but the one associated specifically with radiometric decay rates. A lot of those guys just kind of a priori assume that it's a flood issue. Right. But the rate project, and I read through, I want to say Andrew Snelling's work, or maybe it was Russell Humphreys is probably the one. Yeah, it was Russell Humphreys, because it had to do with the helium count in the granites. So the point is, personally, all I've seen so far, the accelerated decay actually applies to creation week, not the flood. Now, has anybody come up with any evidence to say otherwise? I don't know the answer to that. If somebody does have such evidence that they could tie specifically to the flood year, I would be really interested in seeing that. But from the rate project, what I understood is they went to New Mexico, did some drill cores that were on the order of 3,500 feet or 5,000 feet deep. It was pretty deep stuff. And the cores they pulled up were from granite. Well, the thing about the granite is it's basement rock. It has not been through more than one heat cycle, which tells me it's from creation week. If it were, I don't remember what it is, rhyolite or something like that, where it's actually gone through multiple metamorphic stages, you could reasonably associate it with the flood in certain geological context. But from what I've seen so far, all of that evidence is found, and including, there's more than just the helium deal. There's also radio halos, but they're also found in granites, and so it's kind of a similar deal. And while we're on that, I think it's worth mentioning, because anybody who's listening that's really interested in researching this and continuing a discussion on this whole topic of accelerated nuclear decay, when you look at radio halos, if you read close enough and pay attention to the details, what you get the sense of is, should you expect an increased heat during those events? Absolutely. But you also distinctly get a sense of accelerated cooling.
Right.
That's kind of interesting to me. There is obviously some very rapid cooling that's happening in those systems in order to preserve those radio halos.
Well, I think we have good evidence for that, because when it comes to radio halos and even fission tracks, TRock, we understand that those scars or signs in the rocks, they are obliterated at pretty low temperatures, actually. So
they are. So time and temperature both cause a problem.
Right.
For those not familiar with radio halos and fission track dating, rapid cooling is pretty much the only way, because what happens, there's a process called annealing. A lot of people might be familiar with what annealing is in terms of metal work, but annealing process is basically where you're going to heat something up and then either rapidly or slowly cool it. But during that annealing process, you obliterate those evidences. And if the annealing process takes too long, they basically get kind of whitewashed, so to speak, just by staying hot too long.
So would you say that these granite bodies forming quickly, and therefore the super fast radioactive decay that is basically generating these uranium and polonium radio halos, are you placing the origin of those at creation rather than the flood?
Most typically, yes.
Okay. Which would make sense, because the creation week is everything in acceleration, basically.
Right.
Right.
And creation week, because nobody's ever seen a planet form out of nothing, you can have as much heat as you want in creation week, right? Now the Bible actually alludes to the opposite, because the earth was formed in the water and out of the water, but i.e. rapid cooling. But anyway, the point is, you can't have a heat problem in creation week anyway, because hypothetically, from a purely naturalistic, well, barring the fact that you do have the God of the universe as the creator, but you can't have a heat problem in creation week, period.
Well, where you would have accelerated decay, you also, as you pointed out, you also have supercooling. Mm-hmm. And, we wouldn't have this evidence for radio halos and fission tracks if there was as much heat as I think even some of the creationists erroneously have calculated there to be. And of course, the critics, because then we wouldn't, those wouldn't exist. They would have been obliterated, but they are evidence of accelerated decay. So the evidence for accelerated decay is there, whether it's, the creation and the flood, or mostly creation. Those scars and those marks are there, and the critics can't really deal with it. Plus we have the cold slabs that, again, if there was as much heat produced during the flood as the critics want to say, well, then we wouldn't have those cold slabs. They would have been melted. As a matter of fact, the entire planet would have been melted. So I guess my question for you, TRock, then, when you're in a debate or engaging these more militant critics, and they look to the heat problem and say, you know what, TRock, there was heat produced. How do you explain from your model? How do you get rid of that heat, basically?
Yeah, so no, that's a great question. They like to push this issue, but Science 101, you have to have a robust mathematical model of this heat problem to be, like you said, militant that it even exists. And so I would challenge any critic that says there was a heat problem to produce me your robust mathematical model. And I'm going to look at it as soon as I see it. It doesn't matter whether you start with the energy produced by nuclear decay. It's the famous E = mc squared to derive the total amount of heat. It was brought up in one of the debates. You probably remember somebody said something like 23 oceans would be evaporated completely by this alleged heat. Where's your actual mathematical model? You can throw numbers out there all you want, but until you have an actual mathematical model, you're not making a scientific argument. You're making an argument from incredulity and lack of data is what you're doing. But where do I suppose the heat went? Like I said, I think there probably was heat. That's why we have a molten core. There was heat there. That's why we have granite slabs. That's why we have volcanoes. It's why we have a number of features in the earth. So where did all that heat go? Again, it's a creation week deal. You can have as much heat as you think you need, but part of it is probably heat sinked into the iron core. Part of it may have actually been to simply decrease the what's the word I'm looking for? The viscosity, decrease the viscosity of the mantle material.
Right.
So you have no way of knowing these things. What was the viscosity of the mantle material before that accelerated decay? You don't know. And if you don't know the answer to that, then how do you know there was a heat problem at the crust level
Right.
or at the ocean basin level? You don't, because the heat could have been absorbed in changing the viscosity of the mantle. It can also be absorbed in things like we've talked about, the supercooling that's obvious in granite slabs and stuff like that. So when you have supercooling, you can have superheating, and you basically already got a method to conduct the heat away and not make it an issue for any life that you think might have been on Earth.
Exactly. Yeah, there would be a balancing effect there. So during the creation week, we understand with, and I frequently talk about how Adam and Eve would have been created genetically heterozygous rather than homozygous, because it doesn't make sense for God's command to be fruitful and multiply to be carried out through cloning, right? So diversity makes sense, which means if scientists were to genetically test Adam and Eve a moment after creation, what would they find? Well, they'd find pre-existing differences that they would conclude are inherited from past common ancestors, even though Adam and Eve were just created. There were no past common ancestors. So when it comes to the original created rocks, okay, same with, let's say, the original created trees and the leaves, right? The leaves would have chlorophyll. And so the rocks, would you say the rocks would have a mix of, let's say, uranium atoms and lead atoms? Although the uniformitarian scientists would say, okay, this lead must be the result of decay from uranium to lead. But would they be wrong in the same way that they would be wrong to conclude that these pre-existing DNA differences in Adam and Eve were inherited rather than just created? I don't know if that question makes sense, but
yeah, no, I see exactly where you're going with that, and I would totally agree. Yes, it would be wrong for the same reason. It's because they don't know what the starting point is. That was my PowerPoint slide about the primordial isotopes. You don't know where they came from. You don't even know where they came from in the standard mainstream paradigm. They just don't know. So for radiometric dating, however it was that those isotopes originated, they have a process whereby the planet was formed, and then you have some heat, and probably because of the sheer mass and the gravitational pull, you probably get some heating of the material that's there that should have been cold from flying through space for millions of years. Nonetheless, you should get some heat from that. And then they also have in their paradigm where a planetesimal smashed into the Earth to form the moon, which basically turned the entire planet to molten lava again. So which one of those processes didn't disrupt your original starting point? Logically, any one of them would, and you would have no idea how to convert that to a date. So what they have to assume is that, well, that's why the Isochron method was developed in the first place, because they're trying to eliminate some of those assumptions. But as we've found out, that it's really telling the opposite story, that the mixing that I'm supposing should have happened did happen. That's what it's actually telling us.
it's a great response, TRock. Okay, here's a question that comes in from Redefine Living. Question for TRock. When a critic suggests that something has been contaminated in the geological column, what ramifications would that have for dating methods in general?
Well, it goes back to that super subjective idea of who gets to determine what contamination is and what isn't. I mean, if we put a more specific context on it, let's take diamonds, for example. When you carbon-14 date diamonds and they want to say contamination, well, what's the source of the contamination in diamonds? They're too impermeable to have, any kind of contamination seep into them through porosity or anything like that. They're easy to clean. You can clean the surfaces very well. You can get them extremely clean and make contamination a non-issue for diamonds, but yet it's still what they want to say background noise and that kind of thing. In that particular scenario, the ramifications are that either your equipment isn't all that good, or your lab techs don't know what they're doing, or you have some uncontrollable problem that you don't know how to weed out of any of your samples, the ones that you think are good dates or otherwise. It doesn't matter. It means you've got a problem you can't control anywhere. Other types of contamination might be something like, I don't know, carbon-14 in dinosaur soft tissue, or carbon-14 in coal beds, for example. Now that type of C14 contamination could come from groundwater and porosity, right? That has a different ramification. That ramification is that when you go to carbon date anything that's permeable, like coal or dinosaur soft tissue, you can never control the contamination. You never know what part is contamination, what part is native to the sample. And so the ramifications are deep, and every particular scenario has its own repercussions like that. So yeah, it's pretty obvious that citing contamination when something's not correct really only leads to more problems.
Right. It's like it's a ripple effect, and it's a good question you asked. Who's in the position to say which sample is contaminated, because the C14 in diamonds, like you're pointing out, which is just a fantastic line of evidence for a young Earth, is the fact that there shouldn't be any C14 if these diamonds were billions of years old. And yet it's not just a little bit that's detective. I mean, these radiocarbon labs are reporting, I believe, more than 10 times the detection limit. And
so as I've seen, go down to like the low 30,000s or so in diamonds.
Yeah. So, I mean, how it's not like it's just trace.
No, not at all.
It's quite a lot. And to just chalk this up to contamination every time when you find C14 in samples that you shouldn't find them in, the question we're asking as skeptics is this really contamination? What's the justification for that?
So in diamonds in particular, some skeptic out there might say, well, it's not actually contamination in diamonds, it's background.
Background.
Okay. Yeah. If it's background, here's the problem I have with that. If it were legitimately background that they were picking up, that means you actually do have a way to calibrate it out of other samples. And if you have a way of calibrating it out of other samples that are not diamond, that means you have a way of calibrating it out of diamonds too, and you should still get a net zero. Right. But that's not what happens. So even the background contamination really doesn't make any logical sense.
Well, in my studies on this, we've done quite a few programs in detail. These radiocarbon labs, I mean, they subject these samples to some really, really harsh treatments, where by the time, the instruments are tested with these samples, the samples should yield zero radiocarbon. I mean, they're blank samples. So, yep. Contamination or this background detection really doesn't work. And then the other argument that I've heard, I'm curious what your thoughts are. Dr. Hugh Ross likes to say, especially, he made this argument in his debate with Dr. Jason Lau, that nearby nuclear material could recharge the C14 in diamonds.
Yeah, that's a pretty bad argument, I think. And I think Dr. Jason Lau did a really good job of debunking that idea, because it's what they call neutron bombardment, I believe. And the idea is that some radioactive element ejects a neutron and it slams into, some nitrogen bearing substance and converts it to carbon-14 the same way it happens in the atmosphere, right? The problem is that the rate of that type of decay is, I want to say the number is like 13,000 times slower than the decay rate for carbon-14. And at that, you also have to assume basically 100% accuracy on every single neutron that flies off off of an atom in order to get any kind of discernible effect out of it. So it's just a bizarre, I don't know.
It's an old Earth creationist simply not wanting to tap out on the exact line of evidence that you would expect to be there if the Earth really was young, because the rate team looked into this argument, as they have with all of them, and they estimated, TRock, that you would need 13,000 times more nuclear material in the nearby rocks to adequately recharge the C14.
Yep. Yeah, and they have to be nearby. That's the other point is you have to have that substance pretty close by, otherwise it hits something else first.
Right. So, I strongly believe that the C14 that we find in coal, in diamonds, in fossilized wood, so on and so forth, where it shouldn't be, is just a fatal blow to deep time evolution, for sure.
Yeah, and something that's not actually mentioned very often, but should be it should be fairly obvious to the deep time advocates, and that is that in the YEC position, by default, there has only been one complete plus maybe a tiny fraction, but one complete carbon-14 half-life cycle. So by default, whether you know anything about carbon-14 or not, as soon as you know that basic fact, the first thing you have to conclude is that anything that normally has carbon-14 in it, you should be able to go out in nature and find carbon-14 in it. And that's exactly what we do find.
Right. I'll pretend to be the evolutionist here. We'll give the audience a little bit of a debate here. So, as we like to point out, I typically like to point out, okay, carbon decays so rapidly that, let's say every single atom in the universe was made of carbon, it would all decay within a million years easily. Okay, that's even giving them more than they deserve. But let's say in a million years, it should all have decayed. So if these rocks and fossils and diamonds and so on and so forth really were millions to billions of years old, they should have no carbon left. But yet, we carbon date them, and we get detectable levels of radiocarbon in all sorts of these fossils and diamonds and coal and so on and so forth. But the evolutionists will respond, TRock. They'll typically say, well, okay, for sake of argument, we'll give you that. But, 50,000 years, let's say, is still a lot more than 6,000 to 7,000 years. So they'll say, even with this argument, it still refutes a young Earth. And obviously, they're not getting the argument. But how would you respond, TRock?
So yeah, no, that's a great question. It really is, because a lot of people want to point that out and say, okay, well, exactly what you said. Your biblical history can't be true either. Then, so it's kind of like they're playing the middleman, so to speak, right, and saying, okay, so if you've disproved my 4.5 billion year old Earth, I've also disproved your 6,000 year old Earth. Well, how do I respond to that? It's the same problem. This question you have up on screen alludes to the exact same thing, and that it goes back to the extrapolation. You're talking about still gaining C14 through natural processes, basically the energy from the sun striking nitrogen in the atmosphere. That's the process which you create nitrogen or C14 de novo. It's not, the system's not balanced yet. So what they're doing is they're extrapolating that basic idea of how C14 is created in the atmosphere. They're extrapolating that into the past. But as I've already pointed out, that type of extrapolation absolutely does not work in real application physics. It only works on pen and paper or on a calculator where you're just crunching numbers. And to put a finer point on that, the reason that type of extrapolation can predictably fail is because there are other things that can affect the carbon balance besides the sunlight striking the Earth's atmosphere. And that has to do with the relative amount of vegetation on the planet. So if you have an ice age, for example, where roughly a third of the planet was one time covered in ice, you've basically buried a whole bunch of vegetation. You've buried almost a third of it, or possibly more than that. When you get rid of all that vegetation in a very short time span, you're disrupting the carbon balance, because those plants have to take in the carbon from the atmosphere. And if they quit taking carbon in from the atmosphere because they're dead or covered up or whatever, your carbon-12, carbon-14 balance is going to get out of whack real quick. Another type of historic event that we know has happened that will also disrupt the carbon balance is desertification. So if you have wide-scale desertification like what's happened in Egypt, you can pull up a globe of the Earth and see this band across a certain between certain latitudes, and see this desertification across the globe. And when that happens, it's the same thing as the Ice Age problem. You're wiping out a whole bunch of vegetation and changing the C12, C14 balance. So no, give me a 30,000, 40,000, 50,000 carbon date, and I'm just going to tell you you're running into the same extrapolation errors that all the other systems run into.
Right. Great point. So many great points. And, you know, according to the young Earth creation model, we're not expecting that, you know, these dates are just going to fall right on to 6,000 years every time. I mean, the further we go back into time, right? Let's say we go back a few thousand years closer to the flood. Well, we're going to get a lot older ages than true ages. And so the carbon dating will tend to give ages that are far too old, especially the closer you get to the flood, right? Because, you know, we're looking at changes in the magnetic field decay, and also the flood changed. It would have buried a lot of lots of carbon in the environment. Yeah, go ahead.
Absolutely, yeah. The flood is the same as the Ice Age and the desertification problem, except it's the entire planet all at once. So it's got to have the biggest impact on how you would conceivably calibrate a C14 curve across the, you know, a span of years.
Exactly. Okay, so here's a question. Well, I guess we did kind of just touch on this for a while. Why should we be surprised by finding carbon-14 in things like coal, diamonds, and oil, since they were all made by living things like plants? If there's anything else you wanted to add to it, TRock, I know we've touched on this pretty thoroughly.
Yeah, this does kind of highlight one of the deals. The secularists should be surprised, because diamonds, it doesn't matter what they're made of. When it's no longer living, it can no longer take in carbon-14. And if it can no longer take in carbon-14, then all that you have is what's in there, and it's going to decay away, and it's never going to be replenished. So it has to go away in that same time span that you expect it to. You know, they say 50,000 years is the detectable limit. Okay, I'll double that and say 100,000 years later, diamonds should not have anything at all that you can reasonably measure, because every one of those, it's the same problem. They quit taking in carbon-14 from the atmosphere, and all you have is what was left in them at the instant that you know, organism died that formed that substance. That's all you had to work with. You don't get any new carbon-14 to continue the decay process.
And I want to note, especially for any critics that just think that it's, you know, it's an anomaly. It's not. You know, these scientists, they have sent off all sorts of samples to be tested. And these were samples ranging from tens of millions of years to hundreds of millions of years. And guess what? They all came back the same age. They all had radiocarbon in them. And these rescue devices that we've touched on tonight, TRock, they don't work. They don't work. And then they can't address these observations, this data, and then they run to what? Isochron dating, which you have so you know, beautifully pointed out, has its own list of problems, has its own set of discordant dates.
Yep. Yeah, no, so it's like kind of like the highlight of all that is a question I like to ask skeptics. If you, let's say you dig up a piece of charred wood out of an igneous rock sample. If you carbon date the wood, you're going to get, let's say, 20, 30,000 years old, okay? If you radiometric date the igneous sample, what are you going to get? 2 million years, you know, 1.5 million years. Most volcanoes today are considered to be like in the 2 million or less range. So I'll say, let's say you get a million and a half years out of that. Now you've got two conflicting dates. Which one are you going to trust? Well, what if you found some historic writing where, and just purely hypothetical, but what if you found some historic writing where some Roman soldier wrote a letter to Caesar and said, "Hey, I need some financial help here. This volcano erupted in my field and destroyed my crops and my tools and my house and everything. Send some aid." Now you have 3 different dates. You've got a carbon-14 date, a radiometric date such as potassium argon, and then you also have a written record. Which one is the geologist going to go with? 100% every single time he's going to go with the written human record.
Exactly. Great points. Yeah. TRock, this has been great. I'm looking through the questions here, and I think we hit them all. It was a technical but necessary, a very important show. We've spent an hour and a half just absolutely demolishing, isochron dating and other dating duds. None of them work. As we've pointed out, carbon dating. Carbon is a creationist best friend. We've dealt with all their rescue devices and mechanisms. The isochron dating doesn't work. You've debated conspiracy cats on this issue, TRock. What were his best responses or rebuttals to what you were saying? And then what's a good way to refute those if we haven't yet touched on them?
No, that's a great question, but ironically, he actually did not contest hardly anything I said.
Oh, wow.
If you go find that on his, what's his channel? Agree to Disagree.
Right.
Is the one he has that posted on. If you go find that, you'll find that he doesn't actually contest anything I said about isochron dating, which I thought was a little surprising. But then if you watched his opening, he didn't really talk about the dating method itself. He really just gave a kind of a chemistry overview at like a high school or junior high school level.
Right.
So
like how it works theoretically.
Yeah. So because he didn't really contest anything, I can't answer the end of your question. But I have talked to people who do try and prop up the method. And so basically the only thing I could ever get out of anybody that actually knew a little something about it was that the method was self-checking, which I kind of alluded to that in my slide. The method is self-checking because the ratios are supposed to remain constant over time. So it kind of checks for those basic assumptions that you can't validate with single isochron methods. So that's their response, is it's self-checking. But that's all they can say about it. But then when the rubber meets the road, you go out and you find discordant dates all the time, and hence that long list of terms around false isochrons that actually exist in the open literature that tells you they can't tell the difference between a mixing line and a real isochron. They have to basically start guessing based on the geological context instead.
Yeah, that's a great point. I'm finding not a lot of sophisticated engagement from the critics. I mean, we have now for what seems to be a couple of years addressed very comprehensively their best responses to, for example, these arguments pertaining to like C14. Right. I mean, we've addressed the background detection argument. We've addressed the contamination argument. We've addressed this claim that says that nearby material could recharge the C14. We've addressed it all, but yet it doesn't stop them from still repeating what I like to call already debunked talking points. Here's a final question that comes to my mind as we hit the hour and a half mark, TRock. I do appreciate your time, brother. When it comes to these rocks that are being tested, where we know when they were formed, recent volcanic eruptions, and then they yield erroneous dates of millions to billions of years old. I've heard some of your critics say, well, of course you're getting millions of years old on these newly formed rocks because you're testing them wrong. You're not supposed to date newly formed rocks. You're supposed to wait, a million years, essentially.
Yeah, so I think 200,000 years is the lower limit that they give. No, that's a great question, because I've heard that so much too, and it's weird when I think about it. I just think it's a weird question, and for 2 reasons. I mentioned this in my presentation earlier. One is, why do you have to know the age before you pick the method. Now, I didn't pull it in. I should have probably done this, but you can go on YouTube and you can you look at some of the university presentations that PhD lecturers are giving on radiometric dating, and they will tell you this method for this date range, this method for that date range. And I gave a couple of those. So my first question is, why do you have to know the age first before you pick a method? And then the second one is, what that questioner is actually ignoring is that in the scientific method, you need a control group. The control group is one where you have every single parameter of the experiment well defined, well understood, well documented, and you know exactly what to expect from what you have in your control group. And then the things that are outside of your experiment group is what you don't know all the variables up front on. And so what they're saying is, don't use a control group to test the validity of radiocarbon or radiometric dating. Now, wait a minute. I thought you were advocating science here. If you're advocating science, you have to have your control group. And so it kind of shows that almost nothing in evolution, deep time, geohistory, that sort of thing, uses a valid control group. They don't have one.
Yeah, it's a great time to be a young Earth creationist. It's not a good time to be an evolutionist. To show the audience what, we spent a lot of time talking about, for example, here, young rocks from recent eruptions yield greatly exaggerated apparent ages. It's not just creationists making this up, right? TRock, these are secular scientists, and this data can be retrieved from what? From mainstream scientific journals. Okay, this is when lava extrude, 1959, 1915, 1792, so on and so forth. You can go through all these, and we're getting dates of 1 million years to 30 million years to almost 50 million years. And so like you said, it's a weird question. It's a weird objection. And to me, it just demonstrates the circular reasoning behind the evolutionists, TRock. Right. Assume deep time to prove deep time, basically.
Yeah, no, that chart you showed up would be really interesting to me, to also add a column that shows which method it was. Was it a single isotope method, or was it an isochron method, or whatever? Which method was used that derived each one of those dates that actually are known from known modern history, or some kind of recorded history anyway. And so that would be the control group. You would set up a chart like that and say, okay, I got Mount St. Helens, I've got Mount Vesuvius, I've got whatever. You got this big long list, and then you show all the different methods and multiple methods for each site. And then you show which method and what the results were. And as a matter of fact, for any one method that you pick, like say potassium argon, super common, how many samples at that one site did you take, and what did the data scatter like in that one method? And then pick 4, 5, 6, 8 different methods and do that on every one of them. That would be a legitimate control group for discovering the validity of radiometric dating. But my challenge to the skeptics is, show me where anybody's actually done that in the open literature.
Amen. Well said, TRock. That's a good place, I think, to wrap it up. This has been an hour and a half on just dismantling dating methods. So to the audience, this is an important topic. This is some technical, and this is some, in my opinion, irrefutable data that shows just how flawed the dating methods are, including isochron dating, which has been kind of held up lately as their best. And TRock, you've done a fantastic job showing that no, isochron dating doesn't work either, and the evidence best fits. The most parsimonious explanation is the Earth is young, consistent with the Bible's account of origin. So, brother, again, thank you so much for your time. Thank you so much for joining us this week for our Defending Genesis Conference 2022. TRock, I want to give you the floor if there's any final words, final thoughts, any final points you wanted to make.
Yeah, no, thank you, Donnie, for putting this all together, the entire conference, not just this one deal. The entire conference, I think, like you said, is really, really important, because the whole point is to defend Genesis, the historic reality of Genesis. And so the one we really should be thanking is Jesus, the Creator, for
Amen.
preserving his word the way he has. We wouldn't be able to do this if the Bible hadn't been preserved the way it was. And then we can take consistent scientific methods and apply them, and find out that when you actually are scientifically consistent, you cannot come up with a contradiction to biblical history. And that, of course, all the thanks goes and the glory goes to God for that.
Amen, brother. Amen. All the glory to God. Doki Doki Bible Club. That's right. Matt Man tomorrow with a presentation at 6, Genesis Genetics. It's going to be another comprehensive program. And then at 10, we're going to have CJ Cox presenting on countering compromise. Today we've had over 4 hours. So please, do share this content around. We started the day with Sal Jardina, a must-watch presentation, followed by a discussion, a great discussion. And then, of course, TRock, the Isochron method, and other dating duds. So thank you, everybody, for tuning in. And again, share this content around. Thank you so much for all your input, engagement, and questions. And we shall see you tomorrow for day 2 of Defending Genesis 2022. God bless everybody. And again, TRock, thank you so much, brother.